Of course, that joke as soon as I start class. This is awesome. Good morning, everyone.
Good morning.
I'm gonna have 8 of you in here right now. Anybody have any questions before we get started? I did note, hopefully you noticed that I did change what we're gonna do this week. I just changed it in Canvas about 20 minutes ago. So this week we're not doing the linear graphing. We're actually going to do error propagation, which I'm trying to implement at least for our 241 and 242 courses over the next semester or so. And if not that, it might also be for 201 and 202 as well. Mainly because we did this when I was at Chapel Hill, and we did that for the equivalent of 201 and 202 as well as 241 and 242. And it really is a more robust way of dealing with experimental data as opposed to using sig figs. That's, you know, the real world scientists don't really use sig figs. We then probably use sig figs just as something to help you with the homework systems and making sure you have the right number of digits and you round off properly there. But other than that, we won't use them. So I'm in the process of implementing that, and I've been teaching it for about the last 2 years, teaching it in all my classes anyways. So I'm going to go on today and show you about propagation of error, how you're really supposed to do that, and propagation of error formulas and how to analyze data and stuff like that. So that's what we're doing today instead of the linear graphing. So does anybody have any questions before we get started on all that? All right. So we're up to 9 people in the class now. So that's a little better. Now I have a really bad example of a centimeter measuring device, but it's really bright, so it shows up well. And then I got a really good example of a measuring device, but it doesn't show up well in the camera. So I'm going to use the really bright, but not that nice measuring device. Okay. But anyways, when you're in a lab situation and you really want to measure something pretty precisely, but don't really want to go as far as vernier calipers, a good steel ruler like this would probably be your best bet. Notice also it doesn't have the 0. Make sure I look at the right end. Yeah. Notice also that the 0 does not start at the end. It's actually got a little gap, and then there's a 0, and there's a little gap, and there's the last one. That's ideally what you want to do, because if you're actually using like a meter stick where the end of the meter, the 0 part and the other end is at the end of the stick, then obviously over time that stick will get mauled and you'll lose track of where 0 is. If you ever have to make those measurements, then you just want to start it from like 1 centimeter and remember to subtract the 1 centimeter when you make the measurement. So that's what we're going to start off with. And it looks like all of a sudden I've got the sniffles, so that's going to make it even more fun because I'm running out of breath trying not to sniffle so much. Does anyone have any questions before we get cracking? All right. Well, I'm going to start off with just a little discussion. I'm also going to pull back and forth between, or go back and forth, I should say, between a document right here. I think it's here. A document that you're going to be working on for this lab. So I'm going to have this document open, and every now and then I'll refer to it, but really it's a document that's in your module for this week, and it's called Error Propagation Part 1.2. And the 0.2 just means that I corrected a couple typos in it. So it's nothing fancy, but we hopefully we'll have another assignment later on that, but I'm not certain of that. So occasionally I'll share screen so I can show you that, but right now I'm going to talk about measurements. So we've done this before, at least in talking about sig figs and stuff like that, but I want to reiterate it. So you can see with this device, I have 0 and then 1, and you might not be able to see it now, but when I put it up close, you can see that between 0 and 1, or between 1 and 2, or between 8 and 9, there's actually 10 spaces in there. Okay. So the first thing you should do whenever you're using a measuring device like a meter stick or a ruler is first estimate what it looks like to be 1 unit. So 1 unit in this case is about as wide as my fingernail, a little bit less wide because my index finger is a little big, but about the same width as my pinky nail. And therefore I know that's about a centimeter. So this should be a centimeter scale. And then if you look at the other end, ideally it would say centimeter at one side or the other. This one doesn't. Again, this is not a really good measuring device. So that's the first thing you do. The other thing you do is you look for the zero. Where's the zero on this? Well, it's not that end. It is right there. And notice it's not on the end of the measuring device. So that's a good thing. But we see where the zero is now. With vernier calipers, what you got to do is move this lever back and forth until a line lined up with zero. And then you realize, oh, okay, that's zero when it's completely closed. And you say, okay, well, what's one? And you roll it across until that same line that was touching the zero is now touching the one. And that's how you figure that out. Third thing you do after you found the zero and what the measurements are in is you count the number of divisions between one unit and the next. So for instance, between 2 and 3 or 0 and 1 or whatever. And you can see right here that there's actually 10 divisions and you make note of them. So if you go from 2 to the next one to what I'm seeing on my board as to its right. Okay, so I don't know if you are seeing to its right or to its left is the 3. Hopefully you are seeing to the right is the 3. But if you go one space to the next little line after the 2, that's a space, then there's another one, then there's another one, then there's another one, then there's another one, and then there's a longer line. Now that longer line usually means half. Sometimes it'll be a little line and maybe it'll be a quarter or something. So that's what happens with the inch scales, for instance. They have quarters and eighths and stuff like that. But in this type of system, you just count the spaces. And in this case, I got 10 spaces between the 2 and the 3. And it looks like at the end of the 5th space is a long line. So that tells me that one's the 5. So if you try to read from left to right, from 2 to 3, it should be 2.0 is the long line that hits the middle of the 2. 2.1 is the next line, 2.2, 2.3, 2.4, 2.5 is the long line, 2.6, 2.7, 2.8, 2.9, 3.0 is the next long line, and that hits right in the middle of 3. So what we realize is there's 10 spaces between the 2 and the 3. And because of that, we can reach the conclusion that each of those spaces represents 1/10 of a centimeter. So that's in decimals, that's the first decimal place. So this measuring device, which is like a meter stick, is measured down to the nearest 10th of a centimeter. That's what it's actually marked at, okay? Now, when you measure something, that means you should be able to, unless the edge is cattywampus or, got divots in and out where you can't really get a good estimate of exactly what the next decimal place is. Unless that's the case, then if you have a nice square flat edge that doesn't have a angle to it or anything like that, then you should be able to estimate one more decimal place. Because if you look at that, say between 2 and 3, I think you could argue that you'd know the difference between 2.15 and 2.11. You probably would know the difference also between 2.15 and 2.19. You probably wouldn't argue that you know the difference between 2.19 and 2.18. So I doubt your uncertainty is 0.05, but I bet you'd be fairly confident in knowing the difference between 2.19 and 2.17. Again, maybe not the 2.18 and 2.19, but 2.17 and 2.19, you could probably tell the difference between. So that would, cutting that distance in half, you'd see that your uncertainty in that case would be 0.01. So that's what your uncertainty of your measuring device is. And we always have to take that into consideration. So as soon as you start measuring with a device, you want to write down what you think the instrumental uncertainty is for that particular device. If you happen to be measuring something that doesn't have a smooth edge, or for instance, that has a curved edge like that, then that's going to be a little bit of loss in precision just because you're estimating from here to here. Now, if you took another straight edge and laid it here and then had your ruler here, you could maybe minimize that to a little bit. But what if this was actually at an angle instead of exactly perpendicular? And you don't know that unless you do some work to determine it. Well, then you might have to also estimate that maybe your uncertainty is not 0.01, but maybe 0.02 or 0.04. Okay, so that's something you got to do each time with any type of meter stick or centimeter scale or whatever. If it was, on the other hand, instead of rounded but and smooth, if it had divots in it and dents and bumps and jags and jiggers and stuff like that, I think I just made like 4 words up there. Then you'd also take an estimate of how well and how precisely you can measure the end. So if it differs, say, by 0.03 from one part to the next, then maybe you'd say the uncertainty is at least 0.02. Okay, so all that stuff is stuff you got to take into consideration. And generally speaking, if everything's perfect, you can use a vernier caliper or a centimeter scale like this, and you can measure down to 2 decimal places so that the uncertainty is plus or minus 0.01. Okay, that doesn't mean that you can tell the difference between 2.19 and 2.18. That means you can tell the difference between 2.17 and 2.19. That's probably likely. If you don't feel that confident, well, maybe you call it or maybe you call the uncertainty plus or minus 0.02, and that's fine too. But you've got to make that call initially. Okay. Now, here's the deal: when you make that measurement, you shouldn't just measure it one time, especially if it's got some kind of little jagged edge, because you want to measure the width and you want to measure it at all those possible places. And ideally, what you do is do an infinite number of measurements, and then find the best estimate of that measurement. So that's the goal of what you're trying to do with the experiment. Now, if it's not a device like this, like a meter stick or a vernier caliper or something like that, maybe it's a digital device like a multimeter that puts out volts to the nearest hundredths place. Well, then in that case, if it puts out the 2 decimal places, then you call that uncertainty plus or minus 0.01, unless the actual manual or something on the device itself says it's something different than that. But you should always assume 1 in the last decimal place as the instrumental error. Okay, that's the smallest it could be, is 1 in the last decimal place that you can actually read. So for digital devices, you're just going to see how many decimal places it spits out, and you put a 1 in that last digit, and that's the uncertainty, unless the manual says otherwise. With a device like this, you can always go 1 digit beyond what the markings are, because you can always estimate that. And best case scenario is you put a 1 in that digit. Does that make sense to everyone? Okay, so let's imagine we actually do take a measurement. What do we do? How do we report that result? And what is the uncertainty in that result? Because we need to know that, because we're going to take that number. Maybe it's the width of some rectangular solid, and we're going to do the height too, and we're going to do the thickness as well, and we need the volume. Well, you don't normally directly just measure the volume unless you have some kind of device that puts out in space all the planes and stuff like that, and then you could calculate it that way. But normally what you have to do is measure the x, the y, the z. Hopefully it's a 90 by 90 by 90, in other words, 90-degree angles on all of them. And if that's the case, it's just x times y times z would give you the volume. But when you have that formula, v of x, y, z equals x times y times z, what is the error that you spit out? Okay, so that's the stuff we're trying to talk about. That's propagation of error, because x has an error associated with it, y has an error associated with it, and z has an error associated with it. What now is the error in this voltage, or excuse me, in this volume, which is a function of x, y, and z? So let me start off with a simple measurement, and I'm going to share, put on my document cam. I've taken the time to write down some digits. Hopefully they're dark enough where you can see. And hopefully I've got the piece of paper where it's close enough for you to read the digits. I'm going to try to push it down a little bit further just to make sure y'all can see the whole thing. I'm wasting a lot of space by having it some of the desk show. So I'm trying to get it closer so it'll always be fairly good. That's probably a little too close, but if I turn maybe this way, maybe it'll be better. That looks pretty good this way. It's pretty jacked up this way. Okay, and now I want to pull it where I don't see that black part up top. So that's about the best, because the edge of the paper is right here and right here. So that's filling in sort of the maximum that I could. All right, so you can see the numbers are. So this is me, imagine, say, measuring the width of this in centimeters. Clearly it's not right because that's not 32 centimeters from here to here, but that's what you can imagine. And you can imagine I did it with a meter stick. Okay. A meter stick or a scale like this, where we have it marked to the nearest tenth and I'm estimating to the nearest hundredth. Okay. Now, what I could imagine this as is me taking a measurement of X and determining it to be 32.91 centimeters, and then me taking another measurement and determining it to be 33.05 and 32.91 and 32.91 and 33.05 and 32.94, all these, and there's 10 different data values there. Okay. So if that was the case, then that would be pretty straightforward. And if I didn't have this data down here, which we're ignoring for right now, but if I didn't have this data right here, I would just say, okay, well, my most likely estimate of X should really be the average or the mean of all these values. Okay. So I would probably want to report X as, and here's the formula in fancy summation notation. The summation from I equals 1 to 10 of X sub I, where that's X1, that's X2, that's X3, 4, and all the way up to 10, divided by 10. Normally it would be the summation from I equals 1 to N of X sub I over N. But this time I just wanted to iterate that I actually had counted these. There's 10 data points and that sort of thing. So that's why I didn't put the N in there, I put the 10. So that's really called the mean or average. And that would work great, ignoring that second column or second row of data. We could call it, for instance, X bar, or we could call it X in brackets. Both of those are some terminologies that have been used from time to time to represent the average or the mean. Now, the mean is a big phrase. It actually refers to many different types. The mean, median, and mode, for instance, are three different types of average. So you can sort of think of average as, well, what average do we mean? Well, I mean the mean, and that means add them all up and divide by the number. You could also think as the average as the mode. In that case, you put all the number, look at all the numbers and see which one occurs most frequently. That's what mode is. And then the median is when you put them all in order and then you find the middle one. If it's an even number like this is, you have to take the average of the middle two, and that's the median. Okay, we're using the mean because that's normally what you do with nice mathematical stuff like this. Okay, so that's all well and good. Now imagine this, instead of being a bunch of measurements that I took, maybe at different parts. Maybe if this was like 30-some centimeters wide, maybe I measured it here to here and got one of the measurements, and here to here got another, and here to here got another, and here to here got another, here to here got another. And that's how you take into account whether it's got jagged edges or whether the angle is not exactly 90, that kind of thing. So that could be why those numbers are the way they are. But they could be something else too. Maybe I took this thing that I measured and I measured it, say, 100,000 times, and then I took the mean of that and reported that to you. So this is my mean. And then another lab group did their mean, their average, which is in this course, like I said, mean. And this is what they reported. And then another group did that one, another group. So these are what the same device, the same thing we measured. We all measured the same thing, 10 groups of us. And we did 100,000 trials or 100 trials or whatever. And we reported to you a mean. And then we took that mean and we took the standard deviation of those numbers. So the 10 number or the 100 or the 100,000 numbers, however many numbers this group did, which is my group, we would take the mean of that, and that's what we reported. Then we take the standard deviation of it, and then we take that standard deviation and find something called the standard deviation of the mean. And that's called the standard error, which I'm going to teach you in a second. If I gave you that back, then what I'm meaning by that is my group would tell you that X is equal to 32.91 plus or minus 0.08 centimeters. That's what that means with that number below it. Okay, this will be something called the standard error. Okay, which is also called the standard deviation of the mean. And it's given as a symbol sigma x, which is actually the easiest way to write this is it's the standard deviation of x divided by the square root of the number of trials. Okay, so that's really what that is. This would be my mean. So that's how you report.
Your last part.
What's that? Oh, that's sigma. That's a Greek letter sigma with a subscript x. And then that is defined as, so you use three bars instead of two, like in equals. You do s with a subscript x, and that's divided by the square root of n, where n is the number of trials.
Thank you.
No problem. So me as a lab group giving you a number, and I'd say, hey, our lab has determined that the width of this thing is 32.91 centimeters plus or minus 0.08 centimeters. Okay. And really, I probably should put this in parentheses since I only put the centimeters on the end. That's what my lab could report to you. And that's how I would report it. You always put the most probable or best estimate as the number, and then you do plus or minus the standard error. So this would also be called the best estimate. Okay, so that's the mean or the best estimate. Now that I have that, then evidently another group that did 100,000 trials too, well, they reported a 33.05 plus or minus 0.06. And another group did 32.91 plus or minus 0.12. So this might have been a bunch of, freshmen college students or high school seniors, and they got a much worse error because they aren't that good or their equipment was crappy or something, right? That's why the error is so much larger in that one. This must have been like our A team. These were the actual practice experimental scientists that did the best they possibly could. Okay, so now that you have all this data on X, what is the best value? Well, the best value is always essentially the mean, but when you have data like this, which gives you an X value and its error, the best value isn't taking and adding up all of these and dividing by 10. The best value is adding up all of these, but taking into account that this one should have more importance than this one, right? If this group got an error of 0.12, this data point shouldn't have that much weight. Whereas this group got an error of 0.01, that should have a lot of weight, right? And then maybe this group right here should have about a medium amount of weight. So really, the other average is the weighted average, or the weighted mean. So in that case, we would say our best estimate, which I told you before, we can put a bar over it to call it that. I'll say X bar, or X bracket, is equal to, now watch this, this is going to be the summation from I equals 1 to N of X sub I over sigma X sub I squared. And then, because I've screwed everything up, notice this would have like units of centimeters. This would have units of like centimeters squared. So then I'd have units of 1 over centimeters, and I need to put it plus or minus something like that. So if I'm going to do that, I really need to make sure it has the same units as the X did. So you can already see I need to get rid of a centimeter squared in the denominator. And one way you can do that, and this is actually the proper way because it has some meaning, I'm going to divide all this by the summation from I equals 1 to N of 1 over sigma X sub I squared. So what this does, notice by putting the error in the bottom, a really small error, which is like 1/100th, makes this one have a power of 10,000 because 1/100th squared is 1/10,000th in the bottom, and then 1/10,000th being in the bottom means a 10,000 multiplied by the top. So this one will be as if we took this trial 10,000 times. Whereas this one would be 12 100ths. So I would divide this by 12 over 100 and square it. That'd be 144 over 10,000. So I'm going to take and multiply it by 10,000 as well, but then divide it by 144. So it's really going to be quite a bit less weight than 10,000. This one's going to have the weight of 10,000. This one's going to have the weight of 10,000 divided by 144, which is, less than less than 100. So that's pretty significant. And by doing that, I've given more weight to the load error things. And then I've taken out the way I've screwed up the numbers by adding up all the sums of the individual weights squared. Okay, so the individual weights is really the uncertainty 1 over the uncertainty squared. Yes, I always upload these documents. They're always at my Miriam's asking, can I upload this document? Yes, I always upload this document immediately after class, or at worst case is usually within a couple hours after class, to my Google Docs. So, and it'll always be labeled, like in this case, it'll be PHY _241 _L0. I think this is 1C, if I remember correctly. The C is the part you really want to look for. And then it will say 093021. So that date is what you want to do a search for in my Google Docs. And then you just want to make sure you get the right section. You can download the other sections. They're probably doing the same thing for that as dates, but the one for your section will be that. So yeah, it's always in my Google Docs. And one of my students recommended a really cool eraser pen. And look, it looks like a tattoo. Anyways, so I got that. All right. So yes, this will be up there. So that's really the best way to take it. If you have a consorted group of means with their errors, then you want to take the weighted average, and that's the way you calculate the weighted average. So let me show you the difference in these two. I'm going to stop this for a second and do a share screen. And the screen I would like to share is hiding because I have a document up. Oh, there it is. Okay. So these are those X values and those sigma X's that I just had. Okay. Now, if I wanted to, I could do this. Let's first off take this whole bunch of data, Control X, and I'm going to give myself a little bit more space and put it right there. Okay. Now I'll write next to this, I'll write sum. Okay. And then I'm going to say equals sum. And I'll do D4 colon D13. That I could have typed it that way, but I just highlighted it instead. And that gives me the sum of all those. Now I'll say the mean. And this is just a straight mean. This isn't the weighted mean. So I'm going to say this is equal to the sum divided by 10, because I know there's 10 trials. So 32.967 is the mean. But that's just the plain mean. That has nothing to do with the actual weighted mean. Now, if I want to do the weighted mean, I'm going to say sigma squared. So I'll take this and I'll say this is going to be equal to 0.08 squared. And now I just copy that formula down. And when I do that, it'll do it for every one of them. So I now know sigma squared, but remember the mean was supposed to be 1 over sigma squared. So I'll say recip. And that just means the reciprocal of sigma squared. And in that case, I'm going to say equals 1 divided by boom. Now I'll copy that down. And what that is actually those 1 over sigmas for each of the sigmas for each of the x. So, or excuse me, each of those 1 over sigma squared for each of the x's. Now the sum of that is just equals a sum of, and this time it's H4 to H13. So I could type H4 colon H13, and that would be just fine. And you can see now that, for instance, that 32.91 that had an error of 0.01, yeah, it's got a weight of 10,000. The one that had a error of 0.02 has a weight of 2,500. So you can see what I was talking about. By multiplying this value by 2,500, you're making it seem, several times more powerful than this one that's multiplied by 400. And even more times this one that's multiplied by 156.25. So now what I want to do is I want to take the product of sigma or recip and x. So this is what I'm going to do. I'll make that big enough so y'all can read it. Now what I want to do is, remember the formula was the summation of x sub I over sigma x sub I squared. So I've got to take this number 32.91 and multiply it by this number, and that's why I said product. So I'm going to say equals this times this, and that gives me that value. And I repeat that for all of them. Yes.
Should be the reciprocal, not the sigma squared.
Is that what I did? Let me double check my, thanks. That's a good catch if you did. Let's see. D4. Oh yeah. Yeah. Thank you. So yeah, that wasn't supposed to be D4. That was supposed to, or yeah, that was not supposed to be G4. That was supposed to be H4. So what I can do is just change that to H like I do here. And now I'm doing it right. Yeah. I don't know why I did that. I just must have grabbed the wrong one by mistake. But now, yeah, and that makes more sense. Now you see how big this 32.91 with the 0.01 is? It's 329,100. Whereas this 32.91 with the 0.12, that's only 2,285. So you can see how it's giving much more weight to the ones with low error. Now I'm going to take the sum of all this equals sum, and that'll be the numerator of my formula for the weighted average. Okay, and now I will take the weighted mean. I'll write it like this. So this weighted average is going to equal this number divided by this number. So I didn't get a huge difference. I got a difference of, this should be rounded to 32.97 probably. And I'm going to talk more about where we round that to a little bit later. But if I just did the straight mean, I would get 32.97 to 2 decimal places. If I did the weighted mean, I get 32.95 to 2 decimal places. So you can see that the averages did make a difference. The weighted average versus the regular average. And if it happened to be that all of them were the same, then this would give exactly the same number, 32.967. So does that make sense to everyone? So that's the 2 ways you represent your measurement as the best value that you could estimate it to be. Okay, let me stop share. So you've now seen 2 ways to fill in this part of your number. See the 32.91? I could fill it in as the mean, which is what I did first, and I got 32.967. Or I could fill it in as the weighted mean, which I did by getting 32.95. So let me just write those down. This was 32.967, and this was 32.95. I believe, I know the next digit was 0. I just can't remember if this was bigger than 1 or bigger than 5 or 5 or bigger or what. So I'm just going to put a centimeters by both of them. And that's the difference I got. Does that make sense to everyone? All right. So when you report a number, you write the variable. So how to report. A measurement. Or result. X. Okay. Well, what you do is you write X is equal to the average, which I'm going to put in quotation marks because you got to remember, sometimes it's better to use the weighted average, or if you can use a weighted average, then you should. So I'll put this in quotation marks, plus or minus.
You're ready, Professor.
Oh, thank you. Nice. Okay, so you're going to report it as X equals the average, or like I said, if you have the ability, because you actually know individual errors of the measurements, then you do the weighted average, and then plus or minus the either, I'll just call it error, and I'll define what error means. Okay, now error can be the standard error of a large, ideally it's large, number of trials, or the instrumental error. Whichever is largest. So that's a key rule here. Notice I said we were doing this with like a meter stick. So I made these measurements with like a meter stick, which means the best case scenario is my uncertainty is going to be 0.01, because that's the instrumental error. I can't get any better than that. Well, if I did all these fancy statistics doing what I called the standard error, and I got 0.003, then I'd have to use my error as 0.01 here, not 0.003. Because you can never use statistics to get more accuracy than the device actually has that you use to measure it. That makes sense, right? If you have a calculator that only calculates to say 3 decimal places, you can never use statistics to find the average value and get it to them in 4 decimal places. Does that make sense to everyone?
I think so.
Okay. So if we were to look at data in general, like let's say this was 100,000 trials, this was 100,000 trials, this was 100,000 trials, this is 100. All of these are each 100,000 trials. Okay. And then I took those 10 and tried to use those to find out what X really would be. Okay. Well, if I plotted all that data for all those different X values, and I plotted the number of times 32.91 came up versus the number of times 33.05 came up, so on and so forth, then I'd get something that looks a little bit like this, which you guys recognize as a bell curve, right? So this right here is X bar or X bracket. That midpoint, it should be the average, in other words. And if you really want an idea of how good those results were out of those 10, 100,000 trial results, you could really say, well, how far is it from here to here and from here to here? How far are they different from the average value? And the difference between a particular value, let's say this one, and the mean is called the deviation. So you could say the deviation is equal to, let's say, actually, I don't want to use that symbol. I just went dyslexic and made two symbols. I want to use this, the lowercase delta. The delta is defined to be x sub I minus x bar. Okay. So your first instinct might be, well, let's just average how far away each x is from the average. And that would give me an idea of how good this data is. If this data is really narrow, I've really got some good results. If the data is really wide, that means there's a lot of variance in my data and it's not that good. So maybe I say first try to estimate spread, the spread of data. So my first attempt at estimating the spread of the data would be I'd take xi, or let's say x1 minus x bar plus x2 minus x bar plus x3 minus x bar plus dot on up to plus x10 minus x bar. And then I divide that by 10. Okay, if you get rid of those parentheses, I'm going to call this, by the way, just tau, because I don't have a symbol for it, but I want to refer to it with a single letter. So I'm just going to call that tau. That's our first try, which starts with a T, which is like a tau. So if I wrote this without parentheses, what I'd actually get is x1 plus x2 plus x3 plus dot plus x10 minus x bar minus x bar minus x bar minus dot minus x bar. And all this would be over 10. Now, I can see that this right here, if I break this part of the fraction up into x1 plus x2 plus dot plus x10 over 10, then I see that's just going to be my mean. But if I pull the minus out from this fraction, then I'd see x bar plus x bar plus x bar. In fact, I'd have 10 times x bar right there, and that would be over 10. So lo and behold, I get x bar minus x bar, which equals 0. So tau is not a good estimate of the spread. And the reason why is you're just as likely to have the same number of negatives as positives in here, and they all end up adding up to give you 0. Does that make some sense? So the next idea would be, let's try to get rid of those negatives that could screw things up. And the way you could do that is either take the absolute value, which is a pain in the butt, or what we decided on was take the square of that. So what we ended up doing is we defined this thing called S sub x. And that thing is, I'm going to leave a space here because I still got to write some other stuff. I'm going to consider taking the mean of this, but I'm going to do it in such a way that none of these terms are negative. So what I'll do is I'll take x1 minus x bar and I'll square it. Then I'll take x2 minus x bar and I'll square it plus dot plus on up to x10 minus x bar squared. And then instinctively you might say, okay, well, I want to take the average of that, so I'll divide it by 10. Well, then you look at it and you say, oh crap, it's got units of centimeters squared now, because this is a centimeter, that's a centimeter, and this has no units. So you say, well, wait a second, I took the square of it, so I should probably undo that by taking the square root. And I'll put a little prime on there because this is not the right formula. Okay, this is close to the standard deviation. It's what you probably think is the standard deviation, just arguing out. But it turns out this actually gives slightly bad results. Gives slightly bad results. for small samples, sample sizes. So for instance, 10, 25, 5, that sort of thing. Those are fairly small sample sizes. If you really want to use these things as supposed to, the number should be approaching infinity, like the 100,000 and the millions that I was talking about. Those are pretty good. So it was discovered it's best to define the standard deviation not as the sum of the deviations squared divided by n and then take the square root. It's actually the square root of the summation from I equals 1 to n of x sub I minus x bar squared, not over, and notice the square root covers the thing in the denominator too, not over n, but over n minus 1. So that really is the standard deviation that we use. Okay. What's the use of that? Well, remember this curve up here. If you calculate the standard deviation, then 68,100 of the x's will be between x bar minus s sub x and x bar plus s sub x. So you can literally say that 68.1% of all the results from all those trials, every x that all of these people measured, every x, not just these 10, all the x's in this one, all the x's in this one, all the x's in this one, all the x's, all those x's, 68,100 of them out of 100,000 would be within one standard error, standard deviation of the mean. So notice you take x bar, which is the middle, you subtract sx, you get a lower value. You take x bar, which is the middle, and you add sx, you get a higher value. Not only that, I want to say it's 95,400, and it's actually slightly more than that. And actually, I really should write that the other way. Instead of saying that number is bigger, I'm actually need to try to say that the number of data is actually bigger than the 68,100 and bigger than the 95,100. Of those x's will be between x bar minus 2sx and x bar plus 2sx. Okay, so that's what this formula gives you with that correction. And then finally, greater than or equal to about 99,800 of x's will be between x bar minus 3sx and x bar plus 3sx. Okay, so that's what the standard deviation is. It turns out the standard deviation is not that important, except it easily gets us the number that is important. The reason why that's not that important is I don't really care to know what the trials were of these various experiments. I don't care to know how close 68% of the trials for each of these were to the mean. What I really want to know is how close were the means of all these trials to the mean of the whole thing. In other words, when I take the mean of all this, whether it be this mean or the weighted mean, when I take that, how close are all the other total experiments like this to having a mean that large, of that size? Okay, that's why we use something called the standard deviation of the mean. So if I now took and did a plot of the means of all these trials, that brings me to another sheet of paper. Now I'll do a plot of X bars versus number of X bars for all those trials, I'll again get a hopefully Gaussian looking distribution like this, a bell curve. And this is the mean of the mean. So you might write it as X bar or X bar, okay? And then I want to take the standard deviation of this. So the standard deviation of these means is called the standard error. And notice we're now dealing with a really large number. Before, when I just made up the standard deviation formula, I had to do the n-1 in the bottom because we might be dealing with small numbers. But now I'm talking about huge numbers, so I don't have to do that that n-1 anymore. In fact, what I'm going to do is I'm going to say that sigma x, doing the same process we did before, I'm going to take the means now and find their quote unquote standard deviation, only since the means were made of bunches of data and there were bunches of means, then I don't need to correct by that n-1. So I'm going to say now this is equal to the square root of the summation from I equals 1 to n of x sub I minus x bar squared over n and then times n-1. Which makes that formula look really ugly and hard to calculate. But really, if you remember the formula for standard deviation, it just lacked that n. So it really is just the standard deviation divided by the square root of the number of trials. Now, if you did 100,000 of these out of 100,000 means, greater than or approximately 68,100 of them will be between, actually I'll start writing in non-cursive, will be between x bar minus sigma x and x bar plus sigma x. And when you do 2 sigma x's, that means greater than or equal to 95,800. And when you do 3 sigma x, that means greater than or about 99,000. This was supposed to be 400. I don't know why I wrote 800. 99,800 of them. Okay, so when you're trying to report your result, you don't want to know, hey, everybody in the world, I'm telling you that your trials, 68% of your trials will be between this and this. No, what you want to tell the world is, hey, 68,000 or 68.1% of your experiments that the rest of the world does should come up with this value of the x, namely x minus sigma x and x plus sigma x. So in other words, from there to there. So that's what you really write as x is equal to the mean plus or minus standard error, or, well, actually I should say or instrumental error. Okay. So what does that mean? Let me share my screen again and show you how to go about doing this calculation. Does anybody have any questions on that before I do that next part? Okay. So I'm going to take this spreadsheet again, and I've now figured out what the mean is, and then what the weighted average is as well. Okay. Now, what I need to do is actually find out the standard deviation of the X's, and then divide that by the square root of the number of trials. And from that, I can then calculate the standard error. So what I'm going to do is I'm going to make a column over here, and I'm going to say deviation, which remember is X minus X bar, and it's going to be in centimeters. And I'll make it big enough for the box to fit everything. I'll make this one quite a bit smaller, and I'll make these a lot smaller because they're not really that important now. Okay, so what I'm going to do is I'm going to say this is equal to the X value minus the mean, and the mean is right here, or the weighted average is right here. I'm going to stop dealing with the weighted average right now. I just wanted to show you at least one example of how to do the weighted average. We'll very rarely get to do a weighted average. So I'm just going to take this, which is D15, but I'm going to drag this box down. I don't want to do that without putting dollar signs in there. So I'm going to say the D and then dollar sign 15. Okay, so that's my deviation for the first one. And that's my deviation for all of them. Now, deviation squared in centimeters squared. I'm going to make that big enough for us to see it. So I'm now going to take this and say equals this to the 2 power. So now I've got the deviation squared. In other words, from our formula, I got the summation of x sub I minus x bar squared. That's what each of these are, is the xi minus x bar. Now I need to take the sum of those, and that's going to be equal to sum of these guys. And that's the sum of my deviations. Now to get the standard deviation, which comes out in centimeters, I'm going to take that and divide it by n minus 1. So I'm going to say equals this divided by parentheses 10 minus 1 in parentheses. So that says my standard deviation is 0.0039. Now I want to show you this. Let's see. Let's call this Excel standard deviation. I can say equals standard deviation. There's actually several of them. Actually, I want to use this one, standard deviation. So now it just wants my numbers. So I'm going to take these numbers right here and pull them down. And lo and behold, you see they're actually doing a different formula than we did. It looks like they're about a factor of 2 larger. Okay, so that's one of the things you got to find out. What formula is your calculator if you're using that, or your Excel if you're using that? What formula is your calculator or Excel using versus the formula that we used? Now I might have made an error in here somewhere, so that normally I find the standard deviation that Excel does is the exact same one that I do. Somehow this one came up a lot smaller, and I suspect there might be an error somewhere, but I'm just showing you how to do it right now. So we got that. Now what I do need to do is find the standard error, and that's also in centimeters. And remember, the standard error is just the standard deviation divided by n, or the square root of n. So I'm going to take my standard deviation and divide it by square root, SQRT, of 10. Okay.
Did you forget to use the square root for your standard deviation? Or did I just miss that?
Oh yeah. The standard deviation had the square root in it as well as the standard error did. And they're both over the n-1 or the n's in the bottom, but the square root's on that as well. Okay, let me check this. I'm wondering if maybe let's just call this 9 instead of 10 minus 1. Make sure it was doing that right. It does seem to have been doing that right. Let me check the formula that got this. This is the sum of L4. That's right. The L13, that's right. And both of these, when I click on this is K4 squared. So that's right. That's right. All these look good to me. Okay. Let's check my deviations, make sure they were right. I said D4, which is this, minus D15, which is my mean. Okay. And D15 again, D15. Yeah, so that's all those are right. So I don't know why the standard deviation is coming up different. But what we do know is that once you add the standard deviation, and by the way, I'll say Excel stand error in centimeters. So in case the standard deviation is right that the Excel did and I made a mistake, then I'll go ahead and compute it here. This is equal to the Excel standard deviation. Nope, not that. The Excel standard deviation, which was right here. Crap. It's equal to this divided by square root of 10. So, and that looks better to me. That looks like the more likely outcome. So what I'm going to tell you now is when you go to report this, this is where I'm going to teach you about the rounding. So let's say I'm going to assume what I did with Excel was right. So I'm going to write over here on this piece of paper that I'm getting ready to show you. I'm going to write that I got the mean was equal to 32.967. Centimeters. I'm going to say that the standard deviation was equal to, I'm using Excel's one, so that's 0.06254. I'm carrying a bunch of extra digits there. And sigma x according to that is 0.01977, like that, centimeters. Okay, now I'm going to stop sharing and turn it back to my document cam. Okay, so I told you before we're going to deal with how to round this number and that sort of thing. So what you're supposed to do is you now report x is equal to, you take your standard error and you reduce it to 1 digit. Now, if that digit happens to be 1 and the next digit is maybe 4 or higher, then you might want to go ahead and include 2 digits. So I'm going to say this is equal to 32.967 centimeters plus or minus 0.019 centimeters. Okay. Now, what I did was I forced this last digit to be lined up with that last digit, and that's why I rounded it. So no matter what came after this, I would have rounded it to this spot just because I used that. Now, if I'd found instead, like the other one, I'm gonna pull up the other result. According to me, I had X mean was equal to 32.967 centimeters. I had S sub X was equal to 0.0039 122 centimeters, and sigma x was equal to 0.00123 centimeters. Okay. All right. I just wrote that down real quick just from the Excel spreadsheet. I just wanted to go back and refer to that. So I've now written these information down. So if I was using that data as opposed to the standard error, I mean, to the Excel data, then I would report X as 32.9. Now this time I have a 1, but the number after it's not 4. So I would even then I would round it right there. But remember the instrumental uncertainty was equal to plus or minus 0.01. So in this case, my statistics gave me a uncertainty that's smaller than the instrumental error. So I have to use the instrumental error, and this becomes 9.7, by the way. So basically, I again use 1 digit for the error. Since this was 5 or greater, I round that up. And there are ways to stop overcounting the 5. Like some people will say, if this digit is 5 and this one's even, then you round it up. But if this digit's 5 and this digit's odd, then you just call it 96. I'm not going to make you do that, and I'm not going to grade you, take points off for you doing it or for you not doing it. But again, what I did was I took my error to 1 sig fig. The only difference is when it's 1.4 or 1.5, 1.6, 1.7, 1.8, or 1.9, you might do 2. And I made this last digit line up with this last digit. Okay, so that's the way you're really supposed to round your numbers. And notice also that when the standard error came up to be smaller than the instrumental error, I still use the instrumental error. Does that make sense? All right, well, that's the main part of this, is just the statistics side of it. So when you're actually reporting experimental results, and if you see them in journals, they'll always have something like this, plus or minus this. That plus or minus is supposed to be that standard error, which I just taught you how to calculate. And you're going to do that with the lab sheet. That's all going to be done on your own. I'm going to finish this up in a few minutes, and then you guys can start working on that on your own. And you're counted, you get your 50 of your attendance points just for being here today while I was doing this. And then you'll get the other 50 if you turn that lab in a week from today. So let me show you the next part of this. So the next part of this is, let's imagine that we have X is equal to some X bar plus or minus some sigma X. And by the way, even if that's the instrumental error, it's still sigma X. Okay. Yeah, the calculated sigma X was this, but the error or the uncertainty in the measurement is what goes here, and that's called sigma X as well. So I'll just put it like that. Well, if that's the case, and you have to use that X to calculate some F of X like this, okay, you can say, well, this right here is, let's say, X. And this distance from here to here is sigma X. Well, I think you can see that this quantity right here should be the sigma F. Okay. And I think you can see from that sigma F is actually equal to the magnitude of dF of X with respect to X. That's when you have exactly one variable times the sigma X. So that's a error propagation formula for when you have one variable. So for instance, let's say F of X is X in meters. So in other words, what you do is you take X and multiply it by 1 meter divided by 100 centimeters. That would be what your function is. So your derivative of F with respect to X is just 1 meter over 100 centimeters. And of course, that's already positive, so I don't have to worry about the absolute value. So there I would say that my x is, I'm going to convert, or my f of x is, instead of 32.97, it's now 0.3297. And then I would say that is plus or minus sigma f, which is going to be 1/100 times the 0.001. So I'm going to move the decimal 2 places to the left and say this is 0.0001. And now all this can be reported in meters. Okay. So that's how you would report a propagation of error that just came from basically multiplying a x by a conversion factor. Okay, that is literally a formula, so that's perfectly fine. And what I'm telling you is this is sigma f, which equals 1/100 times sigma x. Now that's what happens when you have a function of only one variable. But if you have a more robust function, like let's say the function v of x, y, z, where v is really the volume. Well, in general, what the answer is the uncertainty in f of x, y, z, comma, dot, dot, dot is actually equal to, you take the partial derivative of f with respect to x, you square it, and you multiply it by sigma, the uncertainty in x, squared. Then you add to that the partial derivative of f with respect to y squared, and you multiply that by the uncertainty in y squared, plus the partial of f with respect to z squared, multiplied by the uncertainty in z squared, plus dot, dot, dot for however many variables you have. That's the general formula. Okay, so no matter what function you have, if you have variables in it that have uncertainties, sigma x, sigma y, sigma z, blah, 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 then you have to take this derivative. And don't worry that if you haven't covered partial derivatives, they're literally the easiest thing in the world. I'll show you 2 examples and you'll be good to go. So let me give you an example. Volume as a function of x, y, and z. Well, we know that would be, for instance, if you're talking about a block, like this, where this is x, this is y, and this is z, then the volume would just be x times y times z. So your volume should be reported as x bar times y bar times z bar plus or minus sigma v. So in other words, you're going to take your best value of x, your best value of y, your best value of z, in other words, your means or your weighted means, whatever, and you're going to multiply that, and that'll give you your expected value or your best estimate of the volume. And now you're going to use the error propagation formula to find out this. Well, it turns out the error in v is the partial of v with respect to x squared, I'm going to have a square root in front of all this, times sigma x squared, plus the partial of v with respect to y squared multiplied by sigma y squared, plus the partial of v with respect to z squared sigma z squared. Now, the deal with partial derivatives is if I'm taking the partial derivative with respect to x, and I'm going to pretend y and z are like 2 and 3. Only I can't multiply 2 and 3, so I just have to leave it as 2 times 3 times x. Okay, so what that means is I get the square root of the derivative of 2 times 3 times x is just 2 times 3. So that's in fact y times z times sigma, and this would be squared, of course. So now I got to put a square there, times sigma x squared. And really to do that, obviously, we don't just take a random y. We're going to take the average x and y, just to keep that in mind. Now, when I take the derivative of y with respect, or excuse me, of v with respect to y, now I'm going to pretend like the x and the z are 2 and 3. So I have 2 times 3 times y. That's just going to give me 2 times 3, which is x bar, z bar. And since the formula has to be squared, I had to square those times sigma y squared.
And then I'll say plus finally the partial of v with respect to z. In this case, I'm going to act like everything but z is a 2 or a 3. So it's 2 times 3 times z. So again, we're just going to get x squared with a bar over it, y squared with a bar over it, times sigma z squared. Now that is exactly right. So if you wanted to compute that, you would put in what they reported in front of the plus or minus for y, what they reported for what's in front of the plus or minus for z. Same thing, what's in front of the plus or minus for x, what's in front of the plus or minus for z, what's in front of the plus or minus for x, what's in front of the plus or minus for y, and then what's after the plus or minus goes here for the x, and what's after the plus or minus and the y goes here, and what's after the plus or minus and the z goes here. That's exactly all you have to do. Now, it's ugly, and in fact, there's a nice, neat way of making it better, and it requires us to invent a new symbol, and it's actually already been invented. We call it the fractional error. So the fractional error, which is given the symbol sigma f over f, it's defined this way. You take the uncertainty in f and you divide it by the best value of f. That's sigma f over f. Okay. You could also say sigma x over x is the symbol that you use to label it, but the formula for it is sigma x over x bar. Okay. So by introducing that, we can do something kind of neat. I can take and calculate not sigma v, but sigma v over v, which we know from this means take the uncertainty in v, which would be all this nasty thing, and divide it by the v, which would be x bar, y bar, z bar, like that, right? So that's going to be sigma v over x bar, y bar, z bar. Well, that means I'm going to take the square root, which was y bar squared, z bar squared, sigma x squared, plus x bar squared, z bar squared, sigma y squared, plus x bar squared, y bar squared, sigma z squared. And I'm going to divide it by this, x bar, y bar, z bar. But I really want it under the square root. So the way I put x bar, y bar, z bar under the square root is I square it. And because when you square it and then take the square root, you get exactly what you had before. So I'll put all this over x bar, y bar, z bar. But since I put it under square root, each of those are squared. So now I can say the fractional error in the volume will be, notice this front term, the y and z cancel out with the y and z and just give me sigma x over x bar squared. The second term, the x and z cancel out, so that just gives me sigma y over y bar squared. And this last term, the x and y cancel out, so this just leaves me sigma z over z bar squared. And that is the fractional uncertainty in the volume. But remember, that's also equal to the fractional uncertainty divided by the best volume. So if you take this quantity, which is going to be like 0.0003 or something, and you multiply that by your volume, then you'll get back the thing that goes after the plus or minus. So then you'd say, okay, well, V is equal to X bar times Y bar times Z bar plus or minus this god awful thing, sigma V over V times X bar, Y bar, Z bar. In other words, that's literally what you would calculate. Okay. So this is going to give you a number. You're going to take the best X, the best Y, the best Z, multiply them, and that'll give you a number in cubic centimeters or cubic meters. And then you're going to take and calculate this thing, which is literally the uncertainty in X divided by the best X. the uncertainty in y divided by the best y, and the uncertainty in z divided by the best z, square them, add them up, take the square root, and that's going to go all in here. And then you multiply that by the volume you just put here, and that'll give you the uncertainty in v in cubic centimeters or cubic meters. Okay. So this is the generic formula for error propagation. That's the one you're going to use repeatedly, unless, like I said, unless it's a function of one variable, like this was, then you use then you use that one. Okay. Now, just so you'll know, here's another, let's say f of x, y, z. Let's say that's actually equal to x, y, z squared plus 3z. Just as an example for doing partial derivatives, the partial of f with respect to x, why don't all y'all give that a try? Remember, you're pretending like any variable other than x is in fact a number.
Is that x, y, z squared plus 5z?
Plus 3z, but yeah.
3z.
So hopefully everybody got, hopefully everybody got
yz squared.
Yeah, thank you. Yz squared. What about the partial of f with respect to y? See what y'all get. I'll see what I get, and we see if we agree. And then the partial of f with respect to z. Okay, so I think that's enough of seeing how to do partial derivatives. So I think you should be able to do this now. Now, let me show you something real quick. Has everybody got this copied? Like I said, I'm going to post it in a few minutes, so you don't have to worry about it if you don't get it. But I'm going to go ahead now and share my screen and show you the document we'll be working on. So your lab this week is to, you can rewatch this video because I'm going to post it pretty soon on my YouTube channel. And you can watch this video to find out what you missed, if anything. But you'll see that basically it goes along with what I'm doing here, only I used a different set of numbers here. Okay, so it just talks about all those things that I said, the standard deviation of the mean, the standard deviation, standard error. It gives you rules about your numbers. It gives you the formula for the standard deviation. And then I give you a table. You're going to fill this out by hand. Everybody's got to do this out by hand. And then everybody also has to do the same thing using either your calculator or Excel. But if you do both, I'll give you extra credit. You can take a photograph of your calculator's output if you want to show me that you did it with your calculator. Okay. And then here's the other formulas and things that I introduced. And here's some nice results that you can get. You just saw me do one that's sort of like this. I did X, Y, Z instead of just X, Y. But it's neat because whenever you add, you just get the uncertainties equal to the sum of the squares of the uncertainties. When you subtract, you get the same thing. When you multiply and divide, you get the fractionals. This is supposed to be sigma A over A, by the way. Oops. So I am going to, not that. I just found an error. I'm going to put a big fraction right here. Type in an A there. That was a boo-boo. And I am going to do the same thing here. Nah, jerk. Script. Crap. Okay, so that's good enough anyways. So that's sigma d over d, and obviously this should be sigma v over v, but I'll leave that. So these are some formulas. These are some working it out. What I want you to do is show that this is equal to this is equal to that, this is equal to that, and all that good stuff. And you're going to turn that in. This is where you fill it in your table. And these questions are here, and you just have to do this one problem. Any questions on that?
Do we need to show our calculations for filling out the table?
No, just show your end results. That'll be good enough.
Okay.
Yes, so fill in the blanks of the table, but you don't have to show me the calculations. Any other questions?
So we're only filling in that one table. Then why does the table come up twice?
Up here is already showing you how to use it. If you'll notice down here, I have how to use this table basically. So this is just me showing you how to use it. And then this is where you're going to fill it in down here. So
Okay.
really all in this particular lab, you should turn in everything, but to be honest with you, the part that I'm grading is only going to be from 1 down.
Okay.
Okay.
You want that all handwritten?
Yes, or you can, I don't want you wasting a lot of time typesetting. I don't care if you do, but don't skip steps to save time in typesetting. I'd rather you show me the steps and take a photograph of it by hand and then stick it in there. You can just, hit return after this line right here and leave a big open space and then insert a photograph if you want.
And okay, that makes sense.
Okay. All right. You guys are free to go. Like I said, I'll get your attendance from the Zoom report and you're free to go and holler if you need anything. This will be due at 8:30 a.m. a week from today. I think that's October 6th.
And lab for Excel and the what's it called?
Yeah, the lab for Excel is supposed to be due today at 8:30. The next lab will be the linear graphing, and we're gonna do that next week.
I thought so. So physics lab 4, that's due today.
Yeah, the one we did last week was due today. If unless were you the class that I did lab
No.
5 before it did?
Yeah,
lab
you,
4?
yeah, you
Yeah,
told us
we
to
did.
do,
Okay,
Because you
yeah,
on the
you can have
email
another
says
week
that-
to do lab 4.
today.
Yeah, sorry about that.
Oh, you're
Okay,
good.
just kidding.
I just thought that you had said 2 weeks, so that makes sense now.
Yeah, you can do 2 weeks. I completely forgot about that. And I'd already set it up in the grade book, so it'll know better.
Cool.
Yeah.
Thank you.
Okay, so we got 3 labs due 8:30 next week.
Yeah.
All right, cool. Thank you.
Have a
Fantastic.
good one.
And we can just type in our answers directly onto the table, right?
Yeah,
All right, thank you.
no problem. Have a good one. Alyssa, Tristan, you have any questions?
Absolutely. Alyssa, you want to go first?
I think she might not be there.
Well, I'm gonna wait all day long. Ladies first. I'm just
Yeah, I
kidding.
think she's
Okay.
gone. Alyssa, if you're there, chat something so we'll know. All right.
Okay,
go ahead,
I'm
Tristan.
sorry I was late. I had changed all my early alarms for Thursdays because I changed them